Our next unit is going to be over logic and reasoning. So to start off, we're just going to talk about how to maybe prove or disprove a statement. So the objective is to use patterns to make conjectures, and that I can disprove geometric conjectures using counterexamples. Now what we're going to be using is something called inductive reasoning, and everyday learning goes through this process. As I explain concepts to you, you start to develop patterns in what you're seeing and making a generalization, like an inference or some sort of conclusion that you can draw. That is inductive reasoning, and that's what we're going to be using. Now, these generalizations in math have a special name. These generalizations are called conjectures. Just like a hypothesis in science, conjecture is kind of like an educated guess. We're going to draw a conclusion based on a pattern in data. So we're going to draw a conclusion based on the data that we're given in these figures. Describe how to sketch the fourth figure, then sketch that figure. So we have in figure 1, we have 2 sections. Figure 2, we have 4 sections. Figure 3, we have 6 sections. So notice that each circle is divided into twice as many equal regions as the figure number. So figure 1, we have twice as many, which is 2. Figure 2, 2 times 2 is 4. Figure 3, we have 6, which is 3 times 2. So the fourth figure should be 8 sections, because 4 times 2 is 8. And this is what it should look like. The upper left-hand section above the horizontal should be shaded in, just like they are in figure 3 and 2. So we made that conjecture based on the first 3 figures. And then this is our conjecture that this is what figure 4 should look like. We can also make conclusions on sequences of numbers. So looking at this first sequence, notice we have 6, then 17, then 28, then 39. Well, what's happening here? Notice that for this sequence, we're just adding 11. So finding the next term, I'm going to add 11, and I get 50. For this next one, from 11 to 15, from 15 to 19, 19 to 23, all I'm doing is adding 4 each time. So my next one should be 27. Okay, I want you guys to go ahead and complete these. Go ahead and pause. Your answers should be 14, 16, and 37. All right, in example 2, we're going to describe the pattern. So we need to be describing these patterns in complete sentences. So when we understand what's happening, we can figure out new terms. So notice in this sequence, what's happening is I'm going from -7 to -21 to -63 to -189. And I'm multiplying by 3 each time. So I'm multiplying by 3 to get the next number in the sequence. So from 189, I'm going to multiply by 3 and get -567. Multiply by 3 again, and I get -1,701. The third term that we wanted was multiply times 3 again, and we get -5,103. So we're just using that pattern to then form that conjecture and form the rest of those terms in that sequence, assuming that that pattern continues. Now, some simple conjectures we make every day. Well, if you flip a light switch, you expect that the light will come on. So if I flip the light switch up, then the light will come on. Or if I touch a hot stove, you would expect that you'll burn your hand. Notice that I have these sentences in a specific form. The if-then statement. So like, if that first thing happens, then we assume the second thing will happen. This second part is the conjecture. So then the light will come on, that's the part that we're assuming will happen. That's also the part we have to prove whether or not it's true. So in this example, this is a science example, A scientist dips a platinum wire into a solution containing salt, sodium chloride, passes the wire over a flame, and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt, finding that they all produce an orange-yellow flame. Make a conjecture based on her findings. So again, just like a hypothesis in science, we're making a conjecture. Our conjecture is, well, if the solution contains salt or sodium chloride, then in a flame test it produces an orange-yellow flame. Because we've repeated that finding over and over, we can assume that that might be true. Now again, we haven't proven it, we've assumed it based on observations using inductive reasoning. Okay, so here's kind of where we are so far. We've talked about what is inductive reasoning, what is a conjecture, and now we're going to move into how we actually prove things true or false. Okay, these green statements right here, proving conjectures is very hard. So when we're trying to prove something true, we have to consider every single case. Proving conjectures false is so much easier because all we have to do is find one case where something is untrue. And when we can find that example where something is untrue, that is called a counterexample. Okay? Counterexample is really important. We're going to use these a lot as we work through proofs. I want to prove something is false with an example that shows it. Now, what are the steps for inductive reasoning and how do we use it? We find a pattern, we make a conjecture, and then we test it or find a counterexample. Okay? Now, here's something that you need to take into account. A statement is only true when it's true every time, when there is not a single case where it's false. In order for a statement to be proven false, it only has to be false one time. So we only have to show one counterexample to disprove an entire conjecture. Okay, so we have an example here. Make and test a conjecture about the sum of any three consecutive numbers. Okay, consecutive means in order. So 3, 4, and 5 are consecutive because they're in order. So when we add those together, we get 12. 6 plus 7 plus 8, that's 21. 9 plus 10 plus 11 is 30. 12 plus 13 plus 14 is 39. 0 plus 1 plus 2 equals 3. 20 plus 21 plus 22 is 63. So as we start to look at these sums, we can start to notice a pattern. The pattern that we notice is that each one of these middle numbers, if we just multiply that by 3, we get our total. 4 times 3 is 12. 7 times 3 is 21. This middle number, 10 times 3 is 30. 13 times 3 is 39. So we start to think, well, that pattern keeps appearing in each one of these cases. So I could develop a conjecture that says the sum of any three consecutive numbers is 3 times the middle number. And then I could test that conjecture and come up with more examples. Notice how this gets pretty tedious. We would have to prove every single possible case is true in order to really prove that this conjecture is true. On the other hand, if we look at an example like this, the sum of two numbers is always greater than the larger number. True or false? So we would have to really think about every case where we're adding two numbers, and is it always greater than the larger number? Or instead of trying to think of every single possible case, we can try and think of something that proves it false. So coming up with our counterexample. So as we start to look at this, we start to think, well, if I add a negative number to 0, well, negative 2 plus 0 is negative 2. The sum, or what I get when I add them, is not bigger than 0. 0 is the larger number. So I've proven that this statement is actually false using that example that disproves it. So the sum of two numbers is not always greater than the larger number. In inductive reasoning, we always want to look for a pattern, make a conjecture, and then prove the conjecture or find a counterexample. Proving a conjecture has to do with a formal proof, and we're going to do lots of examples of these as we move through this year. We won't quite get there just yet, but we will eventually. In example 5, show that this is false by finding a counterexample. Two complementary angles are not congruent. So we would want to try and think of a case where two complementary angles are congruent. Well, complementary means to add to 90, so could we find congruent angles that add to 90? Yes. When the angles are both 45 degrees, those congruent angles are complementary. So because we found an example that disproves this statement, that statement is false because this is our counterexample. 45 plus 45 degrees is equal to 90. All right? We have a table of data here. Show that the conjecture is false by finding a counterexample. The monthly high temperature in Miami is never below 90 degrees for 2 months in a row. Well, the monthly high temperatures in January and February were both 89 and 88. So for 2 months in a row, it was below 90 degrees. And so we've proven that conjecture is false based on the data. All right, in example 7, we have a conjecture that says supplementary angles are adjacent. Remember what it means for two angles to be adjacent. They have to share a side and share a vertex. Well, we could come up with two supplementary angles that are non-adjacent. So because we do not have to have adjacent angles, that conjecture is false. Last example. Show that the conjecture is false by finding a counterexample. So based on this data, we want to try to disprove that the radius of every planet in the solar system is less than 50,000 kilometers. Notice it says radius, and our data gives us diameters. So we would have to find the radius of each. Well, remember, the radius is just half the diameter. When we find the radius of both Jupiter and Saturn, we see that theirs are greater than 50,000 kilometers. So because those are greater, we've disproved that all of them are less. So that conjecture is false. In class, we're going to talk about proving conjectures, true or false. Remember, a statement is only true when we can prove it true in every case. But we only need one counterexample to show that a statement is false.